Hello, let's start working on this exercise 14.6. We start with number 4. Find the directional derivative of function f at the given point at the angle theta. Let's see first. We have this function fxy equals to x cubed y to the 4th plus x to the 4th y cubed. The gradient of f will be 3x squared y to the 4th plus 4x cubed y cubed, comma 4x cubed y cubed plus 3x to the 4th y squared. I think that's easy. Okay, and then at 1, 1. So basically the question is, if we have on the domain coordinate 1, 1, and we are moving in the direction that is pi over 6 radian from positive x-axis. Okay, so this is pi over 6 here. This is our x-axis. This is our y-axis. Okay, and this is our coordinate 1, 1. So the gradient of f at 1, 1, that's basically the sum of the coefficient, right? And then the u will therefore cosine pi over 6 sine pi over 6, which is radical 3 over 2 1/2, right? So the direction derivative in the u direction of f at 1, 1 will be 7 dot 1/2 times radical 3, 1. That will be 7/2 radical 3 plus 1. Huh? Okay, that's for number 14. Number 6. So you see how it works, right? So it should not be too hard. So the gradient of the function f will be e to the x cosine y, comma negative e to the x sine y. So if we observe at 0, 0, that will be 1, 0. And the u is equals to cosine pi over 4 sine pi over 4. That is radical 2 over 2 radical 2 over 2. So the directional derivative in the u direction of the function in the direction of 0, 0, I'm sorry, at 0, 0, at the u direction will be 1, 0 dot radical 2 over 2 radical 2 over 2, which is radical 2 over 2. Okay. And then the next part, very similar idea. Find the gradient of the function, evaluate the gradient at point P, and find the rate of change of f at P in the direction factor of the vector u. Which one should I do? I think I will just do number 10 right away. Okay, I will just do number 10 right away. Notice that the u's here are already in unit factor, and keep in mind that's important though. The u already in unit factor. Okay, if it is not unit factor, then you need to make it unit. Okay, yeah, but I will just do number 10 right away. So number 10, part A, what is the gradient of f of x, y, z? If I do derivative respect to x, the x component will be y cube z e to the xyz. If I do the partial respect to y, that will be 2y e to the xyz plus xy squared z e to the xyz, and for the z component that will be xy cube e to the xyz. Now then, part B, what is the evaluate the gradient at point P, f at 0, 1, negative 1. 0, 1, negative 1, that's negative 1. Yeah, the product of x, y, z is 0, right? Okay, and then this is 2, and then this is 0, huh? Yeah, e to the 0 times 1 times negative 1 is e to the 0, which is 1, right? So it's basically y cubed times z, that's negative 1. 2 times 1, that's 2, plus 0, that's 2, and then 0. Yeah, so that's the part B. And then part C, the rate of change, basically the direction, the directional derivative in the u direction of the function at 0, 1, negative 1, that will be the gradient at that point dot the unit direction factor. You will see it's better for me to factor the 1 over 13 out. Okay, so I basically have 1 over 13 and then negative 3 plus 8 plus 0. That's 5 over 13. It's a lot easier to compute. Okay, let's go on. Number 11 to 17, find directional derivative of the function at a given point in the direction of vector v. Notice that vector v here may not be unit, and we need to make it unit first. Which one would you like me to do? Let me do number 14 first then. Number 14. Number 14, we have g of rs, g as a function of rs equals to tangent inverse of rs. Okay, so the gradient of g rs is the derivative of tangent inverse is 1 over 1 plus rs squared times the derivative respect to r, that's s. And then the second part will be r over 1 plus rs squared. Okay, that's the gradient. So at 0.12, the gradient of g at 0.12, that is 2 over 5, right? And this is 1 over 5. Now then vector v equals to 5, 10. Is it right? But I can factor the 5 here, right? So you see the unit factor in the phi direction. You can ignore that 5 and we just make the 1, 2 into a unit. That's 1 over radical 5, 1, 2. Such that the directional derivative of the function g at 1, 2 in the direction of u will be 1/5 of 2, 1 dot 1 over radical 5, 1, 2. That's 4, right? So this is 4 over 5 radical 5, or we can say this is 4 radical 5 over 25. Okay, so you see that the formula is basically the gradient multiplied by the unit vector. Okay, let's go on. Let's try number 16. So the gradient of function of x, y, z. This is, I do the derivative respect to x, that will be yc over 2 square root of xyc, comma, xz over 2 square root of xyz, and then xy over 2 square root of xyz. So the gradient of f at 3, 2, 6, that will be that's 12 over 2 times 6. XYZ is 36, the square root of that is 6. Okay, and then XC, that will be 18 over 2 times 6. This is 6 over 2 times 6. Actually, I can cancel by 6 all of them, huh? Right, I can cancel by 6 all of them. So this becomes 1. That's 3/2. And this is 1/2. Am I right? Now, then factor V is given by -1, -2, 2. So the unit vector of factor V, the length is 9, right? So it becomes, I'm sorry, the length is 1/3. So this is 1/3, -1, -2, 2. I prefer to write it that way. So the directional derivative of the function at 3 to 6 in the direction of unit vector u will be 1, 3/2, 1/2, dot 1/3, -1, -2, 2. Okay, that is equals to 1/3 times -1 minus 3 plus 2. It's -2/3. Okay, let's see number 20. Find the direction of the derivative of that function at that point in the direction of q. The thing is, this is not factor v. Factor v is equals to factor from p to q. So imagine if you have that coordinate 1, -1, 3, that's the coordinate p, and you are going to q. You're going to q. And coordinate q is 2, 4, 5. Now then our factor u, therefore, I'm sorry, factor v, therefore, is 1, 5, 2, right? Okay, now then our unit factor in the direction of v will be square root of what? 30, that's the length. 1 over square root of 30 times 1 factor 1, 5, 2. Okay, now then the gradient of f will be, we do derivative respect to x, that's y, derivative respect to y. Oh, I'm sorry, not only y though, y plus z, y plus z, and then x plus c, and then for the c component there will be x plus y. So the gradient of f at coordinate 1, -1, 3 will be y plus c, this is 2, 4, 0. Then the directional derivative of the function at 1, -1, 3 in the direction of u is 240 dot 1 over radical 30 times 152. That will be 1 over radical 30 and then 2 plus 20, huh? Okay, so that's 22 square root of 30 over 30. That's 11 square root of 30 over 15. That's for number 20. Number 21 to 26, find the maximum rate of change and the direction at which it occurs. So the theory first, given the function, okay, then maximum rate of change is the gradient of the magnitude of gradient of f, right? At that point, at the direction of gradient of f. Okay, that's the idea. So if I do number 24, for example, f of function xyz equals to x plus y over z, then the gradient of the function will be, well, this is x over z plus y over z, right? So this will be 1 over z, and then 1 over z, and then negative x plus y over z squared. Okay, so then the gradient at 1, 1, negative 1 will be negative 1, negative 1, 1, 1, that's 2, that's negative 2, huh? 1, negative 1, negative 1, negative 2. Okay, so maximum rate of change is equal to the magnitude of that vector, which is square root of 6. Direction for maximum rate of change is that 1 over square root of 6 of negative 1, negative 1, negative 2. We need to make it unit, right? Okay. That's for number 24. I think the idea is so simple that I wonder if you need me to do another example. But if you want to, I can. No worries. Number 26. F of PQR equals to the arc tangent of PQR. So the gradient of the function of PQR is QR over 1 plus PQR squared, PR over 1 plus PQR squared, and then PQ over 1 plus PQR squared. So the gradient of the function at coordinate 1 to 1, therefore, is it's 2 over 5. Am I right? The product is 2 squared 4 plus 1 5. Yeah. PR that's 1 over 5, and then PQ that's 2 over 5. So the maximum rate of change, oh, I need to correct this, is equal to 1/5 times the magnitude of, I factor the 1/5 and then I compute this. Okay, which is 3, I believe. So it's 3/5. At most, it changed by 3/5 at the direction of yeah 2 1 2. That's 3. So at the direction of 1/3 of 2 1 2. Okay, so this is maximum rate of change in this direction. Find the direction at which the directional derivative of this function at this point has value 1. Oh, let's find the gradient first. The gradient of xy, function fy, is negative y squared e to the negative xy, and then e to the negative xy minus this times derivative of that negative xy e to the negative xy. So the gradient of the function at 0 2 will be negative 4 and then 1. Now then find the direction at which the directional derivative at this point has value 1. Let's say the direction u equals to AB. Of course, a squared, where the magnitude of u equals to 1. You know what? There are many ways to do this. Let's make it this way instead. Let's make it this way. So I make it what is the best way to do this? I need that to be 1. It's a comma b such that the directional derivative in the due direction of function at 0 comma 2 will be negative 4a plus b. Now I need this to be equal to 1. Let's call that AB to be cosine theta sine theta. Wow. Honestly, I don't know how to do this. 0.02. Let's see. Do I compute it correctly? Yeah, I think I did it right. Okay, so yeah, we need to find the theta, huh? So this is negative 4 cosine theta plus sine theta equals to 1. Of course, one of them is 0 1, right? Okay, one of them is 0 1. Okay, I mean, you make the cosine equals to 0 and then the sine equals to 1. That will work. That's one of them, right? Is there any better way? I want to find a better way to do this, honestly. Seems like not a lot of options, huh? Is it right? Yeah, basically I need to solve this. Let's see. I'm not sure if what I'm about to do next is something you can understand, but there's okay, let me just solve this then. Let me just solve this. So I need more space. How to solve this equation? So I have sine theta equals to 1 plus 4 cosine theta. Square both sides. This is trigonometry. Okay, so when I square both sides, and then I get sine squared theta equals to 1 plus 8 cosine theta plus 16 cosine squared theta. Now this is 1 minus cosine squared theta, right? So the 1 can cancel. So 0 equals to 17 cosine squared theta plus 8 cosine theta. Okay, I can factor the cosine theta. Right? So cosine theta equals to 0. But if cosine theta equals to 0, that basically means my x equals to 0. Right? My x component is 0. Then I cannot run away that sine theta is 1. Right? Supposed to be plus minus 1, but I want to plug that in. I want to plug that in here. You know. Okay, another one is when cosine theta equals to negative 8 over 17, right? Then negative 4 times negative 8 over 17 plus sine theta equals to 1. Basically, then I solve for sine theta. This is 32 over 17 plus sine theta equals to 1. So sine theta equals to negative 15 over 17, right? Such that so the coordinate will be, so from here the coordinate here is 0, 1. That's one way what we expect, right? That's one of the answer we expect. Now the other one is negative 8 over 17, negative 15 over 17. That's the other one. Okay, notice that this has to satisfy two equations. The first one, that the magnitude of u has to be 1, and it also has to satisfy this equation, the second equation here. Okay, so there are two directions at which it goes to give you that direction derivative equals to 1. Okay, let's go more into some applications. Number 30. The temperature at the point is given by this temperature function, where the temperature is measured in degrees Celsius and XYZ in meters. Find the rate of change of temperature at the point P in the direction toward that point. So let's call this point Q here. Okay, so PQ will be 3, negative 3, 3, minus 2, negative 1, 2. That will be 1, negative 2, 1. Okay, so the gradient of t is the derivative with respect to x. So I multiply by negative 2x, right? So multiply by negative 2x. That will be, I wonder if you can understand this, but notice that when I do the derivative of this respect to x and y and z, I must have this function t anyway, right? So let me just put it there. So that will be t times negative 2x, negative 6y, negative 18z. I wonder if you can try to take a look. Okay, so the gradient of the function of the temperature function at 2, negative 1, 2 will be, then let's see what is the temperature at 2, negative 1, 2. The temperature will be 200 e to the negative 4 minus 3 minus 36, huh? See, right? That will be 200 e to the negative 43. Oh, that's very cold, huh? Okay, so that will be 200 e to the negative 43, and then negative 4, 6, negative 36. That's the gradient. I actually can factor the at least 2 out, huh? Oh yeah, we could do that earlier. Oh, anyway, I'll just leave it like that. Now then, how about the direction u? The direction u will be 4, 5, 6, so 1 over square root of 6, 1, negative 2, 1. Okay, so the direction derivative, the rate of change of the temperature at that point P in the direction of U will be equal to 200 e to the negative 43, negative 4, 6, negative 36, dot 1 over square root of 6, 1, negative 2, 1. Now, I hope by taking away the common factor, it's easier for us to compute. So I get negative 4 minus 12 minus 36. Am I right? Okay, that will give me negative 40, 52. So that's negative 200 times 52 over square root of 6e to the 43. I think I can simplify that by that's 5200 over 3, right? I multiply by radical 6 on the top and the bottom, e to the 43. But it is still very, very cold, huh? That's for part A. Part B. While it is very, very cold, imagine if you are at this coordinate here, right? If you're at this coordinate 2, negative 1, 2 with this temperature function, and which direction should you run to increase your temperature the fastest? And of course, the direction will be, the phi direction will be parallel to the gradient, right? At that point, which is 200 e to the negative 43. I can factor the 2 out, negative 2, 3, negative 18. Okay, so the u in the maximum increase will be basically at that direction, negative 2, 3, negative 18. But then I need to divide by the magnitude, right? Like 1 over what? 18 squared is, as I remember, is 324, is it right? Plus 4 plus 9. So what's that? 328 plus 9, that's 337. 1 over square root of 337 times negative 2, 3, negative 18. That's the direction in at which we can increase the temperature the fastest. Okay, and then what is the maximum increase? Well, that the gradient of T at that point. Okay, so which is 200 times 2 times square root of 337 over e to the 43. That's 400 square root of 337 over e to the 43. I hope I don't make miscomputation though anywhere. The number is just too ugly. Yeah, I'm looking at my work just now. Check my computation. Okay, my technique is correct. My technique is correct. I'm sorry, this is negative 2 squared plus 3 squared plus 18 squared. I can do it later. Yeah, check my computation. I don't think I make a mistake, but who knows? Okay, that's the technique. That's for number 32. Number 34. Suppose you are climbing a hill whose shape is given by this equation, where x, y, z are measured in meters, and then you are standing at the point coordinate 60, 49, 66. The positive x-axis points east, and positive y-axis point north, and the position is 60, 40. Okay, now the gradient of z will be negative 0.01 x, negative 0.02 y. Okay, so if I go in the south, that's correspond to 0, negative 1, right? Okay, 0, negative 1. Oh, the gradient z at that coordinate 60, 40 will be 60, 10, 6, negative 0.6, 40, negative 0.8. Okay, so what is the, should you start to ascend or descend at what rate? Well, we will see if it is positive or negative, right? The directional derivative of z at 60, 40 in the direction of 0, negative 1. That will be negative 0.6 comma negative 0.8. That's the gradient dot 0, negative 1. That will give us 0.8. That will be an ascent, which is positive, so it implies ascending, increase. At what rate? At 0.8 meter. At the rate of 0.8. Okay, so basically at that point here, if you go to the south direction, you will increase at 0.8. meters. For every 1 meter you move. Part B, similarly, what happens if we go northwest? Northwest is, that's the direction is negative 1, 1, huh? But we need to divide by the magnitude though. Okay, so the directional derivative at 1 over negative 1 over radical 2, 1 over radical 2 of z at 60, 40 will be negative 0.6, negative 0.8 dot 1 over radical 2, negative 1, 1. Okay, that will give us 1 over radical 2, 0.6 minus 0.8. That is negative 0.2 over radical 2. That's negative. I try to rationalize the denominator. So that will be radical 2 over 10. Because that's negative, then that will be a descending. At the rate of that number, negative square root of 2 over 10. I think part C is the most interesting one. At which direction is the slope largest? What is the rate of ascent in that direction? And what angle above the horizontal does the path in that direction begin? Okay, so the gradient of C, the largest, is when it is parallel, when it is parallel to vector v, right? In other words, our vector v is equal to parallel to negative 0.6, negative 0.8. And I think when we find the magnitude happens to be 1, huh? Yeah, it happens to be 1. Okay. So that's our direction. At what rate? At the rate of that magnitude, which is 1. At what angle above the horizontal path does the direction begin? Now, think of it this way. So this is the horizontal path, okay? And if you go to that direction, you will increase also by 1. Okay? You will also increase by 1. Then what is that angle? Well, the angle equals to tangent inverse of 1, which is pi over 4. Okay? Maybe it's better for us to take a look what the graph look like. Graph of this function look like. Let's take a look at our graph here. So we have z equals to, what's that? Let me see again. 1000 minus. So z equals to 1000 minus 0.0. I'm sorry, I forgot the 0.005 x squared minus 0.01 y squared. Am I correct? Let's see what the graph looks like. Maybe we see it from far away. My bad. Hold on. I want to. Okay, so that's what it looks like. That's what it looks like. Okay, now suppose then I draw a coordinate. Enter. New equation. How do I draw that coordinate? 60, 40. How do I draw coordinate? Honestly I don't know. Yeah, maybe I draw it this way then. I use equation factor. See, it makes me think, huh? Factor equals to 60 and then 40 and then 966. I wonder if it can give us what we need. Oh, that thing is too. No, that's not what I want. I'm sorry. Can I enlarge that a little bit? That dot is way too big. I wonder if I can make it smaller. I'm sorry. This is so messed up. Yeah. Basically, I want to say that at this point, you basically see if you move in the. If I enlarge that again. I want to see that from above. You know what? At least you know what it looks like, right? It's basically a hill. Okay, it's basically a hill. Now, let's go back to our. Let's go back to our nodes. So think of it this way. Think of it this way. Think of it this way. So when we see just the domain, right? 60, 40, 60, 40 here. Okay. Now, in 3-dimension, as you can see earlier, the coordinate is approximately not a good way. Anyways, so the coordinate is approximately, let's say it's here. Okay, and if I do some shadow, let's say that's what the curve look like. Okay, now at this point, at which direction you should go to such that you increase the fastest? And according to our analysis there, we found out that the fastest is actually go in this direction. Okay. Negative 0.6, negative 0, negative 0.6, negative 0.8. kind of like that, in that direction. Okay, now the thing is, like, when you look at the tangent factor here, the factor tangent there, okay, and if I see that from sideways, it will look like this, right? Okay, and according to our theory, it will increase, the ascent will be, it increased by 1, right? Okay, at what direction? What angle? The angle is 45 degrees. But Thomas, how do we know that this is 1 here? Well, remember that we make it phi. This is the phi factor v here, right? Whose length happened to be 1. I mean, we have to make it 1, right? We need to make it 1. Okay, so if I can redraw this, maybe I use this. So kind of like see it this way. This triangle here is this triangle. Okay, if you move in that direction, which is the same direction with this, it will increase by, the slope will be 1. Now that slope 1 has angle, therefore give us 45 degrees. Okay, let's go on. Number 41 to 46, find the equation of the tangent plane and normal plane to the given surface at the specified point. The same situation, right? The same situation. Let's see, which one should I do? I do number 46 right away. Number 46, we have x to the 4th plus y to the 4th plus c to the 4th equals to 3x squared y squared c squared at 1, 1, 1. Okay, define a function, let f x y z equals to x to the 4th plus y to the 4th plus c to the 4th minus 3x squared y squared c squared. Now this gradient of f, now this is equals to 0, right? This gradient of f will then be normal to the surface. If the surface is given by that equation, then it will be normal to that surface. Okay, the gradient of that f therefore is equal to 4x cubed minus 6xy squared c squared, comma 4y cubed minus 6x squared yc squared, 4c cubed minus 6x squared y squared c. Now at 1, 1, 1, we basically add the coefficients. Okay. But for us to find the tangent plane, you remember tangent plane and normal line, we basically need a factor that is parallel to that. So you don't really need to use -1, -2, -2, -2, -2. You can just use the factor parallel to that. Okay, I will just use 1, 1, 1. So the tangent plane, the plane tangent to the surface at 1, 1, 1 must have the position is 1, 1, 1. The direction also parallel to 1, 1, 1. Oh, okay. So it will be x minus 1 plus y minus 1 plus z minus 1 equals to 0. Okay, so x plus y plus z equals to 3. Okay, maybe I mark my 1, 1, 1 here comes from the coordinates, and the coefficient 1, 1, 1 here comes from the first the direction. Okay, the factor normal to it. Now how about the normal line? Normal line Let me call that RT equals to t plus 1, t plus 1, t plus 1. Okay. I think the number happens to be a nice number though. Okay, that's for number 46. Let me just jump to number 51. Show that the equation to the tangent plane of the tangent plane to this ellipsoid at that point can be written that way. So let's see, this x squared over a squared plus y squared over b squared plus c squared over c squared equals to 1. So we let this becomes a function f. So the gradient of f will be 2x over a squared, 2y over b squared, 2z over c squared. Now then, at point x naught, y naught, z naught, x naught, y naught, z naught, then we will get 2x naught over a squared, 2y naught over b squared, 2z naught over c squared, right? Okay, so the tangent plane have this equation: 2x naught over a squared times x minus x naught plus 2y naught over b squared y minus y naught plus 2c naught over c squared z minus c naught equals to 1. I'm sorry, equals to 0, my bad, equals to 0. And then I notice that all of them have common factor 2, so I would just cancel that, right? Because I divide each term by 2, I cancel 2. Okay, then on we have x times x naught over a squared minus x naught squared over a squared plus y naught over b squared minus y naught squared over b squared plus c naught over c squared minus c naught squared over c squared equals 0. Then I collected x naught over a squared plus y naught over b squared plus c naught over c squared equals to x naught squared over a squared plus y naught squared over b squared plus z naught squared over c squared. Now notice that coordinate x naught, y naught, z naught is on the ellipsoid, so it must satisfy this equation, right? Okay, but if you plug x naught, y naught, z naught into that equation, you will get 1, right? Therefore, in other words, this is 1 on the right hand side, and the left hand side, we basically copy paste that. Done. Okay, that's for number 51. We have 2 more questions. Okay, let's try. This section has a lot of exercise though, which in my opinion is nice. Okay, at what point on the paraboloid is the tangent plane parallel to this plane? Okay, so let's call this plane P. Plane P, x plus 2y plus 3z equals to 1. It must be normal to factor 1, 2, 3, right? Okay, now let's set our function f x, y, z equals to x squared minus y plus z squared equals to 0. Now the gradient of this f will be 2x negative 1 to z. Okay, so if the tangent plane is parallel to that plane P, then the normal factors, this guy must be parallel to this also, right? Okay, this is parallel to 1, 2, 3. In other words, there must be a constant k such that 2x negative 1 to c equals to constant multiple of 1, 2, 3. Now let's look for that k first. Okay, let's look for that k first. We have 2x equals to k. Negative 1 equals to 2k. Oh, that one is the one we need. So k equals to negative 1 half, right? Okay, to z equals to 3k. Now from there, then 2x equals to negative 1 half, x equals to negative 1/4. Am I right? And 2z equals to negative 3 halves, z equals to negative 3/4. So we get to x and z already. Now what's the y? The y has to be on that paraboloid, right? Okay, so the y equals to negative 1/4 squared plus negative 3/4 squared. That will be 1 plus 9 over 16. That's 10 over 16. That's 5 over 8. In other words, at what point this paraboloid tangent has the tangent plane parallel to that plane? The point at point negative 1/4, 5/8, and negative 3/4. Okay, would you like to see what it is that? The things we cannot pinpoint that, huh? Let's see. Let's see what is the equation of the tangent plane. Equation of the tangent plane is given by x plus 2y plus 3z equals to constant, call that c. So this is negative 1/4 plus 5/4, that's 1, minus 9/4 equals to c, negative 10. So that's negative 5/4. So c equals to negative 5/4. Okay, let's take a look on our graph. Let's get rid of this. Y equals to x squared plus c squared. Oh, wow, I don't like that. Too much. So I think it opens in the y direction, huh? That's the paraboloid. Now let's see, and then we get to the next one. X plus 2y plus 3z equals to negative 5/4. So that's where it has its. I wonder if you can see that or no, huh? Go backward more. too fast. Maybe we increase a little bit. Can we see that? Do you see that intersection? Let me change the color. Can you see that? That's the intersection. Okay, at that point, see, I purposely make the y values decrease a little bit so that they intersect with the plane at the, not at a point, but at the larger region, larger area, so we can see it better. Yeah, that's where it is. Right? If I make it even smaller, I wonder if we can see it better. Yeah, that's the dot. Right? Can you see that? That's the dot. If I change this to blue, maybe light blue. Ah, no, cannot see better. Yeah, you can see that this is the. If I make it 5, maybe better. Yeah. At that point, okay, it will intersect. Too fast. Yeah, you see. Okay, so I kind of like if I want to see the intersection at the larger one instead of just at a point, I purposely make the paraboloid shift a little bit such that the intersection gets larger. Okay, that's a little explanation about that, what we do there. Last one, number 63. You notice I don't really do problems with odd numbers, right? Okay, but let's take a look. Find the parametric equation of the tangent line to the curve of intersection. So we have two things here. We have two surfaces. The first surface has z equals to x squared plus y squared. And the second surface is 4x squared plus y squared plus c squared equals to 9. Now, if you think about it, this is actually a paraboloid, opens up, right? Okay. And the second one is actually an ellipsoid. Okay, so they intersect at some curves. Let's say the curve looks like, I don't know, the curve maybe something looks like this. Okay, that's the intersection. Now, of course, it's hard to imagine in 3 dimensions, right? But we know one thing that if I say let f1 xyz equals to x squared plus y squared minus c equals to 0, then the gradient of f1 must be perpendicular to the surface 1, right? At any coordinate on that surface. And that will give us 2x, 2y, negative 1. Okay, so at negative 1, 1, 2, it will be negative 2, 2, negative 1. Okay, let function f2 of xyz equals to 4x squared plus y squared plus c squared equals to 9. Then the gradient of f2 will be 8x, 2y, 2z. And this is normal to S2. In other words, the gradient of f2 at negative 1, 1, 2 is negative 8, 2, 4. Okay. Now think of it this way. So one surface, okay, this, like, call this S1. This surface here has normal factor at that point like this. Okay. Now another surface, has normal factor like this. Let's say it looks like this. Okay, now notice that, call this N1 and N2 for example. Notice that the cross product of N1 and N2 must be parallel to the curve of intersection. Can you imagine that? Let's try. I'm trying to graph that though. I'm trying to graph that. So let's say this is the first surface. We know there's a paraboloid. Okay, and then the second surface, that's a ellipsoid, right? So they intersect at this, let's say at this curve here. Maybe I use dot 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 instead for the one behind. Okay, now notice that for the paraboloid, the factor normal at this point, for example, is this, right? And the factor normal to S2 is this one. Now, notice that the cross product at this point will be going into the paper or going into the surface, right? Okay, the cross product. So visually, this is the gradient of F1. This is the gradient of F2. Okay, now the cross product of F1 and F2, gradient of F2 at P, at point P is I j k of F1 is -2 to -1, -8 to 4. That's a factor of 2 actually. I can just factor the 2 out. That is equal to 8 minus -2, that's 10. -8 minus 8, -16, I changed the sign, so positive 16. And then -4 plus 16, that's 12. Okay, so at coordinate P, -1, 1, 2, okay, the tangent line is given by R t equals to the coordinate -1, 1, 2 plus t times 10, 16, 12, or 10t minus 1, 16t plus 1, and then 12t minus 2. Okay, that's the tangent. I think that's all. Okay, I stop here then.